back. We're about to do some weird stuff.
We went to do weird science.
Weird science. Sort of, yeah. We're about to leave Universe 337. We're about to go to a different parallel universe. So let me start off. Before we do that weirdness. Oh, we got to finish this up. I almost forgot. We have one more problem, and then we'll do that. Dadgummit. One more problem, which I do need to review something about. There we go. Okay. Somebody remind me. Let's see. Let's look at this real quick. A little bit of a review. So we have this. Whoa. This formula here. All right, this is going to be a silly question, but can somebody tell me what that formula is for? Be more specific.
Z-score students from the mean to the data point.
No, not the meaning, but what's it for? If I input a raw score, it converts it to a z-score, right? Okay, and you're all like, okay, that's what you wanted me to say, whatever. Like I said before, math most of the time can go both ways. So what if instead I knew a z-score and I wanted to convert it back into a raw score? So we've already done this formula, but I just want you to see yourselves do it without even using a formula. If the mean was 10 and the standard deviation is 3 and the z-score is 2, could anyone tell me where I am? The mean is 10, standard deviation is 3, my z-score is 2. Where am I? Right? Because what z-score means? It means the number of standard deviations away from the mean, right? So I'm 2 of these above the mean because it's positive. So you do 10 plus 2 of these. So 16, right? And of course, we've seen this formula before. It's mu plus z sigma. And if you just do the algebra, add the mean, you get x equals mu plus z sigma. Okay, crazy sauce, right? I like it. Okay, so this is for if I know the raw score already. Like that first problem, we knew it was 27.2, we made it into a z-score, whoop-de-doo. This is for if I know the z-score and I want to work backwards to figure out, in this case, what the time was. So look at this problem here. I want to know the time that represents the 14th percentile. Now here's where this dude really comes into play. Normally, we know the time, we know the raw score, we make it into a z-score, and then we look up the percentage. Now I'm starting with the percentage, correct? 14%. Where's it going to be? Where's the 14th percentile going to be? Yeah, down here somewhere, because I know it's got 14% below it. So now I'm given a percentage. So now I want to do everything backwards. I want to look up the z-score, and then I want to use the inverse function to get back to what a raw score was. So I just do everything we normally do in reverse. So 0.14, don't say anything. Find the z-score and then sit on it for a minute. So if I have an area of 0.14, look up the z-score. Yeah, there's something that's really close. What's the closest area that I see here? I see 0.1401, right? That's the closest I can get to 14%. Are you guys all with me? Bless you. So then that would be a z-score of negative 1.08. So I know this is down 1.08 steps from the mean. So now I can use my backwards formula to figure out what the raw score must be. So I know I'm negative 1.08. That can't be, I always get somebody that tells me the answer is negative 1.08 minutes. I'm like, that is neat. A minute before you got to the college, you found a parking spot. And you're like, hmm. That's cool. I need to be taught. Show me. So now instead I could just say, okay, the mean is, what was it? There it is, 33.74, and I want to go down 1.08 steps. So now I just throw all that in the old calculator. This is where it's nice that it understands order operations. 9.4, 7.4, 20, 24.3, something like that.
24.42.
24.42? Okay, I can live with that. Okay, so if it took me this much time in a week, I would be in the 14th percentile. And in this case, of course, a lower percentile is better. You want it to take less time to find a parking spot, normally. All right, how do you guys feel about that? I think I made a big enough deal of how important this is. Learning how to crawl. This is basic. But of course, for us, it's like, dude, what the hell? It's new to us. This is new to us. But in the grand scheme of things, this is where everything else kind of builds off of. So immediately, we're going to build off of this. All right, so we're going to go to the next level. And somehow, that involves alternate universe Florida. So let me ask you this. If we right now went out and just found one person, we picked one person at random that's on the campus right now, and let's say they're 70 years old, would that really shock us? Like, oh my God. If we picked one person at random, and they were 70, would we all go, oh my God? No, of course not. We're like, okay. Right? Now somebody out there is like, yeah, shocked. It's not the most immediate thing that should happen, but that's not going to freak us out too much. Is that cool? If we went and took a random sample of 30 students and their average age was 70, would that freak us out?
Yes.
What would we start thinking? What's going on today? What's happening? Right? Are we in a weird M. Night Shyamalan movie? Which I never saw that movie. You know what I'm talking about? No? It's probably better you don't. I've heard
Which one? You gotta describe it.
Old. The one where they all get old on the alley. Anyway, don't worry about it. That doesn't matter. If one person being really older than the average age does not freak us out, but a group of 30 having an average age that much above what the average age is supposed to be, that would sort of freak us out. If you went out and took a random sample of people and their average height was 7 foot tall, you'd stop and go, where am I right now? What kind of convention is happening right now? Right? You guys got it with me? A little bit? Okay, so that is an intuitive sense of what we're about to get into. So here's where alternate universe comes into play. Okay. I think I might have, well, I drew a picture sort of like this before, but I can't remember if I called it what I'm going to call it now. Okay. So we travel to Florida in a different dimension. It could be in whatever comic thing you're interested in, multiverse, whatever the shit. And we start walking around. We're in Florida. We start walking around asking people what their age is. And we actually talk to everybody in Florida. And we start, so I ask somebody, how old are you? And they say, I'm 2. So we put a little dot for 2 years old. We ask somebody else, how old are you? I'm 87. Okay, you put 87, right? I'm 90. Sorry. And so we sort of, over time, we build up a distribution that looks like this. Okay. So this is like from 0 years to 100, right? You guys with me? So again, this is an alternate universe because, of course, in Florida, there are people between whatever those ages are. Let's say the mean is actually, yeah, it's a little bit bigger. So let's say the mean is actually like 40. And we'll say the standard deviation, it doesn't matter. It's whatever it is. But within one standard deviation, there's nothing. So that's what I was talking about Chubby Dude a while back. Chevy Chev. I don't know if you guys remember that. That's when I drew this picture, and I don't know if I said what it was. Okay, not amazing. So how did I construct this picture? By putting dots representing people's ages, right? And so there were a lot of people that were around like 15, 20, and there were a lot of people that were around like 80 something, right? You guys with me? Which is roughly like our Universe, Florida, to be honest. It's a bunch of retired people and a bunch of younger people. I did my time in Florida, so moving forward. So this is picking one person at a time and plotting their age. What if instead we took, what do you got, Jeff? Let's say 15 people. So what that means is we're in alternate universe Florida, went through a portal or something, we're there. So of course the first thing you do, as you do when you're in a new universe, is you start asking people how old they are. Normal thing. Every time I've been to an alternate universe, that's what I do. But instead of plotting one person's age, I get a group of 15, and I get their average, and then I plot that. What's going to happen to the picture? What's the most, is it really likely that I randomly pick 15 people who are all right here? Is that really likely? Is that really likely to happen?
No.
Is it likely that I pick 15 Grossmo students who all happen to be 16 years old? No. What's the most likely thing that's going to happen? Am I going to get only young people? Am I going to get only old people? What's the most likely thing to happen? A little bit of both. So the most likely thing to happen is some kind of a mixture, yes? The most likely average I'm going to get is 40. Does that make sense? It should be, it would be, to get an average of 80, I would have had to randomly pick 15 people who are around 80 years old. That is much less likely to happen than getting a mixture and getting close to this. You guys all with me so far? So taking us a group immediately changes what the distribution looks like when I graph those means. This is a picture of a graph made up of individual ages. The graph made up of means of 15 people will look like this, roughly. This highest peak is because the most likely thing to happen is I would get an average close to the real average. Are you guys with me? I really want that to make sense by itself. You go out, take a random group of people. What's your best guess of what their average age is? The average age of the population you pick them from. That's your best guess. It should be close to that. It should be less likely that you happen to pick really older people or really younger people. Should be mixed. Doing good so far? Okay. Whatever this standard deviation was, what is it now? Is it bigger or smaller?
Smaller.
Why smaller?
It's a different
What does standard deviation measure?
spread.
From what?
The mean.
Good. Which one is more spread away from its mean?
Top one.
The top one. You guys agree? All right, some of you guys are kind of like, maybe you'll make sense in a minute. I know. Get over your alternate inverse Florida. I'm sorry. The most likely thing, the highest peak should be right around 40, because the most likely thing is a mixture of both. These two little bumps are kind of related to the next most likely thing is to get people around those two things there. Okay, I like it. Now, here's what gets trippy. I do not care what the original distribution looks like. It could look like insane shit, whatever the hell. The minute I hit something greater than 30, if I take a sample greater than 30, it becomes normal enough. That's a phrase I use a lot. Normal enough for what, Jeff? Well, do we have a chart of answers that only works when I have a normal curve? Yeah, I gave you a chart of all the frickin' answers. But you can only use it if you know it's a normal curve. So if I take a sample and the sample size is more than 30, and I ask about sample means, then I know that it's a normal distribution. Okay, maybe. Was the original normal? Is this normal? So when I plot individuals, it could look like whatever the shit it wants to. The minute it goes above 30, it will be normal. I call it normal enough. Normal enough for what? To use the chart to get answers. Yes?
So would there be a point in your sample size where you have like diminishing returns on the accuracy of what you're trying to measure?
Sure. And real quick, sort of related to that question, how did we determine the greater than 30 by just running a lot of situations through a computer? As I said, computer, here's data. Pick all samples of size 30. Pick every sample of size 30 you can from these millions of data points. And then we did 15, we did 20, we did 25, we did 30. And 30 was where almost everything becomes normal enough. Now let me ask you this. Sort of answer your question. Now I forgot what your question was.
If they're like.
Yeah. Again, the bigger the sample gets, the more normal the distribution becomes. So on day one, we knew a bigger sample was better. We knew that. It's got to be random too, right? So the bigger the sample gets, the more normal the distribution becomes. 30, getting beyond 30 is the magic number where it is normal enough. Yeah, guaranteed to be normal enough. Now, this picture started off not normal at all, correct? Didn't we just do a bunch of problems? Here, how many people did I pick in this problem? One student. But didn't we already know it was normal to begin with? So if it's normal to begin with, I don't care how big my sample is. It's normal. It's only if I don't know if it's normal, I have to get above 30 to be guaranteed that it's normal enough. Okay, maybe. It's getting a little too deep in the weeds, but the prettier the initial picture is, the less n can be, and it gets normal enough. And I've got a concrete example of that. So let me give you this. By the way, if I do n equals 100, now we're starting to get silly. Now it's going to look like this. What is changing? Is the mean changing? And again, this is from earlier this semester when I said if I took the average age of everybody in this room, would it be different if I took two people, their averages, and then averaged all those averages? No, still the same people. So the average of averages must equal the average of the whole thing. That only makes sense. The average doesn't give a shit. What's changing though? What's getting smaller and smaller and smaller? Standard deviation is getting smaller and smaller and smaller. I love it. Okay, so we're actually going to sort of prove what the formula for it is, what the standard deviation becomes. Where have I put all these? Are they up here? Yeah, good. So let me give you this. This is just about my most colorful. Yeah, most colorful, it's got two colors, so watch out. Okay, so alternate universe Florida has way too large of a population. I really want this to make sense. You should have a better feel for this. Since we talked about the choose stuff, like the 80 choose 7, and that's like stupid big number. Remember this? There's a ton of ways. So if I have a large population and I'm picking like 7 people, there's millions of ways to do that. So what I wanted to do for a concrete example was to have a very small population. So we put the numbers 1, 2, 3, 4 on paper in a hat. And of course, the probability of picking any single one of them is 1/4. And if I do graph this where, like rectangles, it does sort of become a uniform. It's not really uniform because it's not continuous, but it's roughly uniform. Are you guys with me so far? Because they all have the same probability of being picked. Now, that's just like alternate universe Florida. Here's the population of Florida. If I pick one person and I plot them, I end up with this picture. Now what we're going to do instead, though, instead of picking one thing at a time, we're going to pick two. So I could reach in, I could pick a 1, drop it back in, and then I could pick a 1 again. I could pick a 1 and a 2 and so forth. So here's all the possible samples of size 2. So again, this is a very small scale example of the problems we're going to do. To make it something we could do concretely on one sheet of paper, I wanted a very small population with a very small sample size. 4 things in my population, sample size of 2. That still ended up making 16 situations. Do you see that? So any bigger, either one of those things, it's going to be really stupid big. So let's not do that. So this is like me asking somebody, how old are you? And they say, I'm 1. So then I plot them, so forth. You with me? So 25% are 1, 25% are 2, so forth. But now I'm going to, instead of doing that, I'm going to pick 2 people at a time. And yes, I could pick the same person twice. And that's related to the picking with replacement versus without replacement thing. Okay, so if I do pick randomly 1 and 1, what's the average of that? 1. Holy crap. Let's keep going. What's the average if I picked 1 and 2? 1.5. 1 and 3? 2. 1 and 4? Yeah, you start to see the pattern. Is everybody with me? Those numbers I'm writing, does everybody understand what they are? They are this. They are the mean. So this is my first sample, and it has a mean of this. Okay. What's the average of 2 and 1? You start to see the pattern pretty quickly. It just increases by 0.5 each time. Right? But I am taking averages. It's just I see a pattern, right? 3 and 1. You see a pattern this way, see? 4 and 1. What is the most likely sample mean? What's the sample mean that happens the most? 2.5, which is the actual original mean, right? Now let me do something real quick before I get too far. From the original population, if I want to calculate the average, I really don't need to do this, but let's just do it for a review. I could do xp of x, right? 0.25, 0.5, 0.75, 1. If I add those up, I do get 2.5. Right? So to get the standard deviation, what column do I need to make now? Does somebody remember? X squared, px. So let's see, let's just multiply these two. So 0.25, 1, oh, I don't know what that is. What is that? 2.75? Is that right? Somebody help me out. And that's 4. Let me double check this. 9 fourths. 2.25, is that right? Yeah, okay, that's better. Thank you. Let me stop for a minute. We're just doing section 4142 for a second right now. And I should get this. Let's see. So when I add these up, I get 7.5, I believe. I don't totally trust myself. 7.5, right? And then the formula for that variance is the sum of these minus the mean squared. So 0.5 minus 2.5 squared. So the variance is 1.25. And if I take the square root of that, I do get 1.118. Okay. Just want to make sure you guys understand. I didn't just pull that out of my ass. That's the actual standard deviation. Now, right now, this is a really strange question. But we're gonna take a sample of size 2, correct? So I'm just curious, out of nowhere, I'm just curious, what is the standard deviation we just got divided by the square root of the sample size? Right, just again, just a normal thing you would wonder about. What is 1.118 divided by the square root of 2? Jeff, you gotta put a 2 in there, buddy. There you go.
7, 9.
Yeah, 791 roughly. Okay, keep that in mind for later. Okay, so that is these numbers in a hat. If I pick many of them, I'll get an average of 2.5 and a standard deviation of 1.118. Okay. Now, instead of looking at individual picks, I'm going to look at the average of 2 picks at a time. So now my distribution looks like this, not like this anymore. My data is now the mean. So what I did was I collected those together. The lowest mean was 1. It occurred 1 time out of 16. Is everybody with me? The next one's 1.5. That occurred 2 times out of 16, 1/8. 2 occurred 3 times out of 16, 0.1, blah, blah, blah. Maybe. Look at the picture now. Does that look more normal? Immediately. Now, again, did our distribution start off nice? Would you say that this is a nice distribution? Right? This was not nice. This was kind of gross. This looks like 2 big piles of potatoes on either side of a thing. This one, uniform, nice. It's already symmetric, correct? I don't need a sample size of 30, above 30, to make me start to look normal. It's already looking pretty normal, yeah? Maybe. Now, real quick, if let me just do it this way, just to remind you guys. We could do everything we did up here, but let me do it like this. Just to remind you, you can do this. If I put this into the calculator, 1, 1.5, 2, 2.5, 3, 3.5, 4, and I put all these in here, hopefully I'm getting them in there right. Does that look right? Let's see. Blah, 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 blah. Yes, okay. No, shit, look at that. I got a 15 up there. That's better. And just to remind you guys, does anyone remember the shortcut that you could use to check work like this? I don't know if you guys remember this. If you go stat, calc, maybe I didn't even show you this. 1 var stats. And this time now, I'm going to put in my frequency list as list 2. Right? This is my frequency list. If I calculate, now I get a mean of 2.5 and a standard deviation of 0.791. Does that look familiar? That's what we got up here, right? I really want this. Right now you're all like, okay, pictures and numbers, great. If I took samples of size 3, do you guys understand how this would become much bigger? This would become much bigger. Couldn't we still do it? Here's the key. I don't need to do all that work. I know that the standard deviation for the new picture, for means, is going to become the old one divided by the square root of the sample size. So if I took samples of size 3, what would the distribution, the standard deviation be for that? It would be 1.118 divided by the square root of 3. So why up here I did square root of 2, because we're going to take samples of size 2. Do I have to do all this crazy ass work every time we have a different sample size? No. Can you imagine a population of 8 million and you took all samples of size 357? Do you want to make a chart? No. So now all I have to do is take the standard deviation of the population divided by the square root of how big my samples are. That is actually, you can, and this is again, I don't know if you guys follow me on this. This is a concrete example of us actually doing it and seeing, yes, it did come out to be that. Okay. So what does this mean for us, Jeff? What am I gonna have to, what kind of weird shit am I gonna have to do? Because right now, if you're a student in this class, right, you're like, okay, that was really strange. We went to alternate universe, Florida. We got this. What is my homework actually going to look like? Okay, that's a really good question. The really funny thing is, alternate universe, Florida, crazy ass thing, barely understanding concepts. The actual change in our work is going to be stupid tiny. The only thing that's going to change is the standard deviation. So let me do an example problem. Let me do it up on the board because I'm getting tired of this projector. So when a sample is taken and they ask a question about the probability of a sample mean doing something, the first thing we have to do is change the standard deviation they gave me. And why is that? Well, let's do a problem real quick. So let's say the mean on a test was 74 and the standard deviation was 11.2, right? And I know, let's say right now, let me do two different things. We know that they're normally distributed. Question 1 says, what's the probability that one student got a grade above 80? Did I take a sample?
At some point.
I haven't taken a sample. I said probably that one student has a grade above 80. Have I taken a sample of students? No. Am I asking about the sample mean? Well, no, because you don't have a sample, Jeff. This is just like what we were doing earlier. Can you draw the picture? Yeah, what goes in the middle? 74. 80 goes about here, and I want to know greater than that, right? This is a quick little review of the stuff we already did. So if I'm given a mean, a standard deviation, I know it's normal, and they ask me a probability question, I can catch that in a picture. And again, I already know the answer is going to be less than half, less than 50%, right? What's the immediate next step?
Find the standard deviation for 80.
No. All right,
Or the z-score for 80.
find the z-score. Have I taken a sample yet? No. Am I asking about the sample mean? No. So I don't need to do the stuff we talked about yet. So here I'm just going to make a z-score. My data minus the middle divided by the standard deviation. So the standard deviation that I'm given is how spread out individuals are. Whenever I'm given a standard deviation like this, it's how spread out individual scores or individual whatevers are.
The z-score is like blind spot.
And the z-score would be where a certain specific individual would sit. Yes. So just hang on. We'll see what the difference is. When do we have to do the weird shit we just talked about? Not yet. Somebody got this z-score for me. Sounds right. 5.4 then, right? So if you look that up, get an area. I don't know what I've done with them. There. 2946. What? Oh wait. So this one, you got 7054 down here. Let me look at 0.54. Let's see. 0.54. Yeah, 7054.
Negative.
No, the areas can't be negative.
Oh, I didn't put it backwards. No.
Oh, you had a negative. Oh, that's why you got the answer. And then, of course, to get the other side, you just do 1 minus this. Is everybody with me? So this first problem was just a trip down memory lane. Remember way back when at the beginning of class, we did these problems, right? Here's what it's going to look like. So again, 1 minus that is 2946, 11. So this is equal to 0.2946, bam. Now, here's what the question would look like. Here's what you look for to tell you to change the standard deviation. We take a sample of 21 students. What is the probability that the sample mean is greater than 80? if the mean of everybody is 74, should it be easier for one person to have an average of 80 or for 21 people to have an average of 80 or above 80? That might be a little weird question, I don't know. Would it be weirder to pick one person who scored above 80 if the mean is 74 or 21 people that scored above 80?
21.
Yeah, okay, so this probably should be smaller than this one. In fact, so did we take a sample? Yes. Are we asking about the sample mean? Yes. If those two things happen, I can't use this. This is the spread of individuals. We need the spread of groups of 21. I need to know how spread out, if I plot groups of 21, how spread out are they? That is what this formula does. It takes the individual spread and converts it into a spread for groups of size n. Okay. What happened? I don't know. Some giant's trying to pick us up. I'm sure it'll be fun. So I take the old standard deviation, what I call the old standard deviation, and then divide it by the square root of 1. 21, yeah, that's the sample size. So somebody help me out there. Is that 2.4?
2.444.
Square root of 21, right?
Yeah, 444? Neato, okay. I'm easily amused. How much work have we done yet on this problem? Not much, right? We immediately changed the standard deviation. Why? I took a sample. I asked about the sample mean. So I cannot use this. I know I keep saying this over and over. It's like a teaching thing. This is the spread for individuals. We're asking about groups at a time. Okay, I need the spread for groups now, and that's what that formula does. Now I do all the same damn work. I do everything the same. Picture, normal, mean is 74. I'm interested in 80. Want to know the area above, make it into a z-score. So my data point minus the mean divided by the spread, which is now 2.444. Yes?
So at the beginning of the equation we did sigma is equal to sigma over square root of n. Should we use the lowercase s for standard deviation of a sample?
Oh, I see what you mean. No, okay. Let me see if I can get this. Okay. I'm so happy you asked that question, because this happens. I'm not making this into a sample standard deviation. Did I take a group of 21 students and calculate the spread for those 21 students? No. That would have been S. If I had the 21 students' grades and I calculated their standard deviation, it would have been the spread of individuals in a sample. Oh, shit. Stay with me. What this formula does is, if I took every frickin' group of 21 students that I could, every possible group of 21, and I plotted them, what would be the spread of that picture? That is still a population, is it not? Didn't I just say all groups of size 21? That is a population standard deviation. Oh, I gotta be careful. I'm sorry. This is so silly, Jeff. I can't have this. Okay. Really important. There. That's the symbol. This means the standard deviation of sample means.
Oh, okay.
Yeah, that would have been helpful if I remembered it. So this is the standard deviation of sample means.
Okay.
So again, this is a population standard deviation, but that's how spread out individuals are in a population. This is a population standard deviation of how spread out groups of size 21 are compared to all groups of size 21. Okay, maybe.
So you're just basically like look at one section of that graph.
Say again?
You're just looking at like that one.
No,
section
sorry.
of the distribution.
So this is the individuals that I've plotted, right? So this person made, really bad grade, this person made close to the average, blah, blah, and that's how I kind of developed this. This picture is made by taking every group of 21. What's your average grade, everybody? 70. What's your average grade, everybody? 78 or whatever, right? And then I build it up from there. So technically, this should be skinnier because the spread would get smaller. But again, you don't have to be that technical in your pictures. How else can I say this? I just had something. Shoot. I really want this to make nothing but sense. So, that's our data point we're curious about, right? And there it is. What is all this other shit? What is all this? What is this? What is all this other stuff? It's all the other test grades for all the other people, correct? Do we know them? Do we know the test grades for all the other people? Do you know the test grade for anybody? No, we don't need to, because again, we're given the two most important things. Now I know, I don't know what the grades are that any individual person made, but I know how they're distributed. So I can talk about areas to one side or the other of something. Here, this picture was constructed by taking a group of 21 and plotting their average and doing that for every group of 21. And then our specific group of 21, we're curious how likely is it they would fall here? And that would be the area that's spot. Now, again, if I'm talking about picking one person, I'm going to use the standard deviation they give me because that's the standard deviation for individuals. If they're talking about a group of size, whatever, I need to change that. I need the spread for groups. Now, let me ask you this. Why is it okay this is not greater than 30?
Because you're looking at the
Because what was it already from the beginning?
74.
It was already normally distributed, right? So we're going to do a problem where I don't tell you. So real quick, just to finish this out, the only new step, the work we did here is going to be exactly the same as the work there, except we're just not going to use this. We're going to figure out the new one and use that instead. All the steps are the same after that. So how long has it taken me to describe the concept? You're all like, a long time. You said a lot. What actually happens nuts and bolts for us? Barely anything. But again, what's the trigger? When do you know to do this? I take a sample, I ask about the sample mean. That's when you know to change it. I need the new spread. So what is this?
That's the
No, I mean, what's the number? Sorry.
2.45.
2.45? 45. Is that right? And then if you look that up, what do you get? Sorry. 9929? Does that sound good? I'm crowdsourcing all my stuff. So then 0.0071. So is it more likely to get one person who made more than an 80 or 21 people who averaged more than an 80? Which one's more likely?
one person.
One person. Why does it make sense? Because if I take a group of 21, it gets smushed. Group of 21 will look more like this. Do you see how little there is here? Where'd it go? 0.7% out here. Because it did get smushed. Everything we just discussed is called the central limit theorem. Yeah. Affectionately known as the chicken, lettuce, and tomato, but that's all right. CLT. Sometimes they'll abbreviate it as CLT. Central limit theorem, or chicken, lettuce, tomato if it's getting close to lunchtime. Okay, maybe. So why is it called central limit theorem? Well, what happens if I keep getting bigger, more and more, a bigger sample? What happens to the picture?
Nothing.
No, if I take a bigger sample and plot the means, the picture keeps getting skinnier and skinnier and skinnier and skinnier. If I take the entire population, won't it just be a straight line at the... So that's in the limit. As I take larger samples, it tends to go to the center. Central limit theorem. Math people, we have very interesting ways to name things. That's one of our better ones, I think. All right, so let's do this. Where did I put them? Did I print them out? That would be really useful. I don't think I did. Why didn't I do that? All right, that's okay. I'll make some examples up.
Did you want the stuff that's on the other side?
No, the other side, to be honest, it was just more practice on chapter 6. For your notes, everything we just discussed here is chapter 7. By the way, most of these, chapter 5, chapter 6, chapter 7, they have like 2 or 3 sections. So they're very small chapters. So just so you don't feel like we're doing an insane amount, yeah.
Did you print out the practice tests?
I did. I have them here. Thank you, though. So I had another handout that I guess I didn't print out, which is fine. Devin. So we'll just make another example real quick, and then we'll call it a day, I think. So let's do an example like this. Mean number of hot dogs eaten in the contest was 16.93 with a standard deviation of 3.917. Yeah, nice and gross. Everybody with me. So there's a hot dog eating contest. A lot of people joined, and the mean number of hot dogs eaten was 16.93, standard deviation of 3.917. We take a sample of 38 participants. So this is a huge thing. This is like from all over the world. Right? It's the World Championships of Hot Dog Eating. It was on ESPN 5, I think. That's a joke just for me. So there's like, thousands of people that join. So we take a group of 38 people. What is the probability that the sample mean time for these people was less than 15 minutes? I'm talking about number of the sample mean number of hot dogs eaten. I was going to do time and I changed my mind. Is less than 15 hot dogs. What's the very, very first thing you should do and why? Okay, I actually like that. So there's 2 possible answers. So drawing a picture, not a bad idea. Oh, but to be honest, why do you know how to draw the picture? Why do I know to make the picture look like this? Do I say anywhere that it's normal? Nope. Oh shit.
There's 38 participants.
Say again.
There's 38 participants. So over 31, you would assume it would be
Our n is greater than 30. That's the magic number. So if I said we pick one person, what's the probability they ate less than 15 hot dogs? You could not answer that. You could not answer that. You have no freaking idea because they didn't give you enough information. We don't know it's normal. I have no idea what it looks like. I have no idea where the probabilities are. I don't know a damn thing. But if I ask you the probability of a sample of 38 people, well, when I plot sample means for a group of 38, that picture will be normally distributed because n is more than 30. No matter what it started off looking like, it's going to become normal. Okay. So if this was 25, that would be an evil problem because you can't do shit. I don't like to do that. I'm never going to do that to you on a test where I'm like, you didn't notice. You didn't have to do anything. That would be so evil. So, now I know I can draw it like this. What goes in the middle? 16.93. I'm curious about 15. Area less than. Gonna make a z-score immediately. What am I missing? I don't have something that I need to calculate. You're all like, it's too bad for you, man. What is this? What is this? What is that for? That's the spread of what? That's how spread out what are. No?
Data point?
Sure, but what data points? That's how spread out individuals are. Right? So the average was 60.93. If I ate 20, I'm, within a standard deviation away from that. You guys sort of with me? So that's how spread out individuals are. Are we talking about an individual in this problem? No, we're talking about a group of 38. So can I use this standard deviation? No. I have to get the standard deviation that works for groups of 38. How do I do that? Like that. So again, if I take a sample and I ask a question about the sample mean, a probability question, you've got to figure out what the standard deviation is for that situation. So if I had a list of all the number of hot dogs that all the participants ate, couldn't we do like we did back in section 2.7 and calculate the standard deviation? That would be the standard deviation for individuals. Thank God I could just do this shortcut to figure out what it would have been if I would have taken 38 people at a time. I don't have to actually take 38 people at a time. So whatever the hell that is. 0.651? What is it? Did I completely screw that up?
0.634.
354.
Oh, 6,
355.
3, 5?
Yes.
Okay. I was doing it in my head, so I'm just happy I got close. Okay. And now I can do my normal work. Now I can make a z-score. I can look it up. I can get the area. Right? So now what would the z-score formula look like? What's our data point that we're interested in? 15. So our data point minus the middle divided by the spread. .28. Negative. I'm making that shit up. I have no idea. Negative 3.04?
Yeah.
Man, I was really off. Sad. And then you look that up, you can get the area. Right now it becomes the traditional z-score problem. Like, sure, traditional, we just learned it like earlier today. Yeah, I know. So this is the first tweak to the standard, you're given an X, make it a Z, look it up. This is the first level tweak to that. Is that cool? And how do you know when to do this? If I take a sample and I ask about the sample mean, I've got to use the correct spread then. So what do you guys get for negative 3.04?
0.0012.
Yeah, so very small probability that a group of 38 ate less than 15, because the average is 16.93, so a group of 38 should be close to 16.93. Check. So, what's going to happen? Oh, let me give you guys, here's the practice test. On Monday, we'll have a quiz. I'll bring the handout that I meant to bring today that's got more practice on the central limit stuff. We'll do that, and then we'll just open it up to whatever questions. We'll make a formula sheet just like last time. The answer key for this. Any homework you give me today or anything else, I'll get back to you by Monday. Anything I haven't graded yet, recent stuff, I'll get to you by Monday. So real quick, look here. just to show you an example of what's going on. So we pick one house, and we're talking about the amount of trash people generate. We pick one house, so I'm going to use the standard deviation they gave me because it was calculated from looking at individual houses, how spread out they were. What happens on part D? Yeah, we took a sample. I'm asking about the sample mean, so what's got to change? Standard deviation. The very first thing I should do is take what it was for individual houses divided by the square root of 33. And never forget this, that formula is just a very specific, the technical thing that's happening, but we knew that the spread should get tinier. It should be harder for a group of 80 people to be more than 7 feet tall. The whole thing should kind of shift in. These areas should get tinier, should all shift in. It just makes sense even before we talked about the math of it. And then the math says, yeah, this is exactly how much tinier it gets. So as my sample gets bigger and bigger and bigger, the less likely it should be to get far away from the mean. The whole thing should get skinnier, skinnier, skinnier. And it does so exactly like this. This is the formula for it. Now, on one level, it kind of sucks because, we're teaching in stats. There's no calculus prereq. So we can't even talk about where the shit that came from. But I do want to show you real quick. If I look at the variance instead, I just square both sides. Do you see how that sort of makes more intuitive sense? Like the new standard deviation is, the new variance is the old variance divided by the sample size. And then the square root comes in because to make a standard deviation, I got to take a square root. So very often, the variance's job is it makes more sense doing math to it and then taking square roots to get this. So I don't know if you guys agree with me that this just looks prettier. Take the variance, divided by the sample size, that's your new variance. That becomes this when I look at standard deviation because I've got to take a square root for standard deviations. Okay, I think that's plenty. So the key takeaway is if you understand chapter 6, you almost have to understand chapter 7 because it just adds this one step. That's all the new work in chapter 7 compared to chapter 6 is that one step. Okay, that's enough. And I do want to say one thing. I really appreciate the earlier therapy session. That was good for me. And I also completely am always aware that you all have similar kind of like things happening. So if you ever have some overwhelming something happening and you need a break or you need whatever, just, you don't have to tell me specifics. You just tell me, I've got to be out for a while or something. And I'll work to trying to keep you up, right? Okay. All right, yes? Oh, chapter 4, if I remember correctly. Quiz is on Monday, yeah. Yeah. Just chapter 4. So that would be the XP of X stuff and the binomial stuff. And I'll have the formulas on the quiz. So you don't have to worry about a formula sheet. Test is Thursday. Yeah, you don't want it Tuesday. Tuesday's the 4th of July. So test is Wednesday, sorry. Did I say Thursday? Test is Wednesday, yeah. Wednesday, yeah.
See you tomorrow, or not tomorrow, next week.
Okay, see you then. I know what you mean. I say that all the time. See you, Bob. Sure. See you next week. Thank you.
Good day.
You too. Thank you.
Question for the 4.2 homework. This one about the raffle tickets. Should the CMX be 4 or 1? This is because it should have 4.
Good. To win. So since one ticket, is this the one where you bought 4 tickets?
Yeah.
So one ticket would have a 1 out of 100 chance. So you have a 4 out of 100 chance.
But isn't this column supposed to have?
Yeah. So therefore, this would be 96 out of 100 chance you lose.
Okay.
Yeah. But be really careful also. You paid $20 no matter if you lose or win. So if you are given something that's worth a 150,
You have to subtract.
you actually made a total of 130.
Okay.
Yeah. Okay.
For 73, I want to confirm that it stays continuous.
Oh, totally. Because again,
Yeah, because
it doesn't
everything has
matter.
continuous continuous, it would have to be rounded anyway, right?
Because really, the idea of continuous and discrete is what could it be? So that's why I'm
Yeah.
trying to say, don't look at the number. If I say it's the bag weighs 8 pounds, it's not discrete because it's a whole number. It's continuous because it could be 7.9 pounds.
Yeah, it's like in the end, it's always gonna have to be rounded to something if it's continuous.
Yeah, the way we talk to each other in everyday life. If you
Yeah.
told me that you live 11.587 miles away, I'm gonna be like, I'm
Yeah,
not sure I want to
even so,
talk
that
to
would be rounded.
you. True, even
Yeah.
that's rounded, yeah.
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 Thank you.
Thank you. Where can I put a note? 1.4. Yeah, just let me see. Oh yeah, that was okay. So, can you email me or something? Remind me that we talked about it. Okay, thank you. Otherwise, I'm gonna forget